Alrighty, we are now on to not this one, wrong one, chapter C. So we talked about rational expressions and simplifying things. We simplify expressions. So now we're going to be working with equations. So gonna do a quick little definition. So an equation is a statement that two arithmetic is it supposed to be equations are equal. I think that should be expressions. Where is, yeah, expressions. Like a polynomial that's not equal to anything, like there's no equal sign. So two expressions that are equal, right? So we can say like 4x plus 7 equals 19, right? So we think of x, this little guy right here, that's our unknown. We call that a variable. It can vary. And that's what we don't really know. So the goal is to find the value of x that makes this equation true. So at what point does something times 4 then plus 7 equal 19? Right? We call these values solutions. All right. So there's lots of different ways of solving equations. So we'll just start off with kind of like a basic one and then grow and grow and grow as better as we get. All right. So to solve the equation, we isolate the variable to one side. So we might have different terms that have our unknown x involved with it. So I want to get everything that has x onto one side and everything that doesn't have x onto the other side, right? So that's what we mean by to isolate the variable onto one side. So to isolate our variable, we do the following operations. We'll either add or subtract the same quantity to each side. Remember, if you've ever heard the analogy, it's like a seesaw. I can't just like plus 6 onto one side. Then it's a different equation. It's completely different. You're asking a different question. So what I do to one side, I have to do the other. I have to be fair. Similarly, I need to multiply or divide each side by the same non-zero quantity. If I multiply everything by 0, 0 equals 0, that's boring. I don't care. That also doesn't tell me what x should equal. And I can't divide by 0. So I need to, what I do to one side, I have to do the other for addition, subtraction, multiplication, and division, except if I want to multiply or divide by 0. That's like kind of the only exception. All right, so we're asked to solve 5 times 3, the quantity 3 plus x equal to 9x. We want to isolate the variable, right? So I want to, I like to rewrite the equation so I can write what I'm going to do next to it. I want to isolate my variable to get only x's on left or the right side. Really depends on what you want. Since I always write x equals, I do x on the left side. But it really doesn't matter because you can just a equals b is the same as b equaling a. You can switch it around. All right, so there's lots of different ways to do when you're solving these equations. So some of you might think to divide by 5 here or distribute the 5. I hate fractions. So I like to do that at the very last moment. I don't want to like to work a lot with fractions. So I'm going to distribute the 5. Right? So we're going to go to 3 and go to the x. So that's giving me 15 plus 5x equal to 9x. Now I'm going to add the same quantity to each side to move my term that has just x to the other side with the other term that has an x. So I'm going to subtract 5x from both sides. And I'm subtracting because we're adding 5. There you go. So I get 15 equals 9 minus 5 is 4x. So now I have everything with x onto one side. Now I need to get x alone. So the reason we move everything onto one side is so that I can just have x times something. And opposite of multiplication is division. So I'm going to divide by 4. So divide by 4, and I get x equals 15 fourths. Okay? Doo-doo-doo. Who emailed me? So oh, it just popped up. I think that's it. Ooh, it's one of you guys. Ding. How do I know if this answer is right? Right? I'm just like new on this. I'm like, oh. Sometimes in math we won't have the tools yet to check our answers, but in most of these problems we can check our answers. So, and I mean by most problems in this course, definitely in this. So how to check answer? That is not how you spell that. Plug in for x, right? I found that x equals this number. Well, let me see if these two expressions equal each other when I plug in x. So I get 5, 3 plus 15 over 4. Oops, that's a 4. Equals 9, 15 over 4. Okay, I'm going to distribute the 5. Or, yeah, or we can add on the inside. Let's do PIMDOS first, where we do parentheses first. So 5, what's 3? 3 is the same as, what's 4 times 3? 12 fourths. So that's 12 plus 15, which is 27 over 4 equals 9, 15 over 4. Okay, I'm doing math on the spot. 27 times 5. So 5 times 25 would be 125. So 2 times 5 is 10. So 135. I need to double check that. Woohoo, 135. And this is going to equal 9 times 15, 150 minus 15, 135. Is that up to 9? Is that also 135? Over 4. Yay! Cha-ching! And we did it right. Cool. So that's how we can check our answers. Okay? So along the way of learning how to solve these equations is we also have fun names for these equations. So how to solve a linear equation. So a linear equation, if you know what the equation for a line is, y equals mx plus b, has something to do with that. Specifically though, a linear equation is one variable in an equation that is equivalent to the form of ax plus b equals 0. All right. And the most important thing here is so a and b are numbers. Really any number. Is that there's only x to the first power. There's no x squared. It's not just a constant. It's just x to the first power. Or so just x would be our highest power. Okay? So a and b are real numbers. Oh, I wrote that here. Good job, I can see. And x is the variable. The key technique is to put all variables onto one side. Variables on the one side, right? So we're asked to solve 7x minus 4 equals 3x plus 8. Okay? So 7x minus 4 equals 3x plus 8. So then what happens is we can now kind of do Actually, no, let's still do just one step at a time. So let's get all my variables onto one side. So I'm going to subtract 3x from each side. And I usually like to do the smaller number just so I have a positive. I don't like dividing by negatives. It makes me think too hard. So I like to make it so that when I move the variable over, I'm moving it so that the thing in front of x is positive. It might not always happen, but that's just what I have learned in practice, what works best for me. All right, so minus 3x. Minus 3x. And it's also really good to put it under. See how I put 7x minus 3x there? And like under it right here. So you can kind of go down the line and be like, oh, okay, then that 7 minus 3 is going to be 4x minus 4 equals, that cancels out. And then I get plus 8, so just 8. So that's good about writing it right under the thing that it's, I don't know, but it's similar to, right? So writing a constant under constant, because now I'm going to add 4. So I'll do plus 4, and then under the 8, I'll write plus 4. I wouldn't write plus 4 under the 4x. That's kind of what I'm saying. Again, these are just tips for success. This is not, you must write it this way. No, that's the beauty of mathematics, is that you can do it whichever way your heart desires. All right, great. So now I have variables on one side, constant on the other side. Now I want to get x alone. I've isolated everything that involved the variable. Now I need to isolate the variable itself. So we're going to divide by 4. And 12 divided by 4 is 3. Whee, there we go. All right. So I mentioned earlier that, oh, and again, you can plug x equal to 3 into here, and you will see that that works. Okay. This is the point where I would ask anyone if anyone has questions on this, but you guys can't tell me that. So if you ever have any questions on these, just email me. So I have x divided by 6 plus 2 over 3, so 2/3, equal to 3/4 times x. Two things here. The reason I wrote this problem like this is so you can see the two different ways that I can write variables with fractions. So right here, I wrote 3 divided by 4 times x. That's the same as 3x over 4. Similarly, with x divided by 6, I can write that as 1/6 in front of the x. Similar to how we were factoring rational expressions earlier, how I can, this is like x over 1, right? So I'm just putting those two fractions together and then pulling them apart in some cases. So they're all the same. But I don't like fractions. So what can I multiply by each one of these things to get me out of the fraction world, really? I think I want to multiply everything by 12. All right. So we're going to multiply by 12 to get rid of fractions. So you can write times 12 on each term. You can write times 12 on the one side, times 12 on the other side, or you can put big parentheses about everything and just do times 12. Same thing, right? And that would say like 12x over 6 plus, oh my God, whose alarm's going off? 12 times 2 over 6, which is 12 times 3 over 4, x, right? Same thing. So that's going to give me 2x plus 4, 8. Oh, because that is a 3. Well, let me write this incorrect again. This saves you the time of finding the least common denominator and then multiplying by that. It's the same thing. And you guys will get better with that as we work on practicing all this stuff. Okay, what is 12 divided by 3? That is 4. 4 times 2 is 8. 12 divided by 3. 3 times 2 is 9. So 9x. Great. This so much more clear. I don't know if that's proper English. That to me looks so much easier to work with than that is. I think we could all agree on that. All right. So we'll just kind of do what we've been doing, move everything with the variable onto one side versus the other, right? So I'm going to subtract 2x from both sides. So I'll get 8 equal to 7x, and then divide by 7, not 8. What am I doing? Divide by 7, and that'll give me x equals 8/7. And you can even go back up here and double check because you're like, oh, what if I put in the wrong, see how I like wrote that wrong? And that's a good way to catch your writing errors because like, I mean, you see them, I do them. And it's always good to check because there are cases that you might get a solution, but it might be mysterious. And I'll show you a case where that is, right? So we should always check your solutions. Even if you don't make a mistake, you might discover what is called an extraneous solution. Let me actually Google what the definition is. I believe it's a solution that actually doesn't exist. Extraneous solution. It is a solution such as that an equation emerges from a process of solving an equation, but not a valid solution to the problem. So, right, what's happening is we're accidentally multiplying or dividing by 0 in some case, right? That was our one exemption is we cannot multiply or divide by 0. Okay, so that's where extraneous solutions arrives. So it means there's an error that we didn't really actually see. Okay, so I want to solve 2 plus 5 divided by x minus 4 equal to x plus 1 divided by x minus 4. So everything has x minus 4 in the denominator except for 2, but that's fine. I'm not going to go through the whole process of like, oh, x minus 4 times blah, 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 and then combining them. And then it's kind of what we did earlier where we can just multiply by x minus 4. So we're going to multiply by x minus 4. So we'll go 2, 5, x minus 4, oops, equals x plus 1, x minus 4. And you're like, oh, multiplying everything by x minus 4, but it'll be fine because it's really only going to affect that 2, and it's going to cancel out each one of them here. So I'll get 2 x minus 4 plus 5 x minus 4 divided by x minus 4. We just talked about simplifying rational expressions. So it should be clear that this equals to 5. And then x plus 1 divided by x minus 4. And then again times x minus 4. They also cancel out, so we're given x plus 1. Beautiful. I'm going to distribute this 2. So I get 2x minus 8 plus 5 equals x plus 1. So that's 2x minus 3 equals x plus 1. Subtract the x, and then if you want, you could do it all at once. So minus x and then plus 3. So I get 2 minus x will just give me x, and x equals 4. All right, but if we go to check, I'll get 2 plus 5, 4 minus 4 equal to x plus 1, 4 minus 4, which will give me 2 plus 5 divided by 0. Oh, sorry, that x should be a 4. Whatever. 5 over 0. and we can't divide by 0. So what do we say when that happens? Do I say extraneous solution? No. What we're going to say is no solution. Okay? So that's why it's always good to check, especially if you see something where my variable, my unknown, is in the denominator. That kind of rings a bell that if I get something, I need to check that I'm not dividing by 0. Because what's happening here is, remember, we can't multiply anything by 0. So what I find x equal to 4, that means up in this step, I'm multiplying by 0, and that's not allowed. So that makes the whole process crumble down. Okay? Oh, that's where I wanted to plug into our solution. And I always miss that part. Okay, cool. So we've talked about linear equations, so now let's talk about power equations. I've seen these be a little bit more troublesome than linear equations. So a power equation is x raised to the n equals some number a. That should not be a big x. There should be little x's, but whatever. So like x squared equal 3, x cubed equals 500. Those are power equations. Which similar, you can do x to the 5th minus 7 equals 4. Power equations, okay? Something like that. So now I have x to some value eventually will equal some constant. Again, the power equations, I'm only gonna have really one x involved. I'm not gonna have x squared plus x like we saw with when we were factoring. I'm just gonna have one x involved, and it's gonna have a different power, not 1, just because that would not be very fun. All right, so for x raised to the n equals a, the solution options are x equal to the nth root if n is odd, and x equal to plus or minus the nth root of a if n is even. It's more and a is greater than 0. And I believe we've talked about this before, that cube roots, fifth roots, seventh roots, and then even if I raise something to that power, the negative involved goes along with it. But if I'm squaring something, raising it to the 4th power, and it's a negative number, it's always going to come out positive. So when I want to find the square root of that positive number, it can be a negative number or a positive number. But if I want to take an even root, so square root, 4 root, 100th root, and that number is negative, the equation has what is called no real solution. And I'm really emphasizing the real part of it. So we just saw extraneous situation where there's no solution. And now if I'm taking the square root of something or even root of something that is negative, there's no real solution. And that's because of imaginary numbers, right? So like -1 equals I, imaginary, which is beyond the scope of this class. Don't use in this class. They're really cool. I was the best and complex numbers, imaginary numbers in my first year, just not to brag. But that's way, way, way beyond the scope of this course. So I'm not even talking about that anymore. Okay. So there's a difference between no solution, no real solution. And I am a little bit of not usually a stickler about most things like that, but there is a solution. There's just no real solution. Remember, we only deal with real numbers. And I'm showing you what an imaginary number looks like. It's something where I have a negative in the square root. Okay. So now we're asked to solve x to the 5th equals 3nths. So the reason that we get this structure right here, that if I'm given this power equation, these are my solutions, is because I want an answer. You see how each of these x's is like basically raised to the 1st power. I want x to be raised to the first power. Right now it's raised to the fifth power. So what can I do to 5 to make it look like 1? Well, I can multiply it by its reciprocal, right? So if I do 5 times 1 over fifth, that just equals 1. Well, 5 is up in the denominator, not denominator, up in, I usually call these like the clouds, up in the clouds, in the exponent place. Well, I know that if I write something like this, oops, x to the fifth to the 1/5, we have that exponent rule that I can multiply those exponents together. But again, remember what I do from one side, I need to do to the other. So I'll do 32 to the 1/5. And remember the exponent 1 over 5 is the same as writing the fifth root. So that's all we're doing. I really like to do it in the exponent though, because what if we had something like 5/4? Then the reciprocal would be 4 over 5. And it would work differently with exponents. Go back and look at, I believe it's chapter, I don't know, A or B2. My heart is feeling like it's in the A chapter. Okay, anyways. So that's why it's kind of good to use this notation rather than I like to call it the radical notation. So then I'll get x to the 5 times 1/5, 32 to the 5th. So this is odd. So I'm taking an odd root. So nothing pretty spectacular about that. So it's gonna be a positive number. If you had not memorized by now, 32's fifth root is 2. So I'm actually just gonna get a positive 2. And then we said 5 times 1 is 5/4. So that tells me that x to the 1 is 2, which is the same as just saying x is equal to 2. And we can go ahead and check that again by saying x to the 5th is 32. Beautiful, right? What about x to the 4th equaling 16? So I would do the 4th root of x to the 4th, a 4th root of 16. 4 is an even number. So x would equal not just 2, but plus or minus 2. And that means there's two solutions, -2 and +2. So I can go in here and I say, oh, -2. Remember, I need that parentheses if there's a negative involved to specify what my base to my exponent is. So that -2 to the 4th is going to be -2, -2, -2, -2, which is 4 times 4, which is 16. Hi, face. And then you can check it with 2 as well. So check. Oh, this my face was already there for that. Great. So that wasn't that bad. We didn't have any negative numbers. Had a root, even root, but it was fine. All right, so now let's do the fifth root, sorry, x to the 5th equaling -32. I would do it the same way. I could do the 5th root, x to the 5th to one side. I can even write it like this. I can switch it up if I wanted to. And vice versa. So again, I'm just going to get x equals, but what? I'm going to get -2, +2. I'm going to get -2. All right. And that again comes from, if you think about it, negative, like right here, see how I have an even number. So each negative cancels out with another negative. This one cancels out this one cancels out this one. But when I have an odd number, these two make 4, these two make +4. Oops, that guy forgot it's negative. And that guy is still negative. Positive times a positive times a negative. It's going to give me a negative. So that's why odd powers and odd roots carry the negative through. And it's also why even roots do not. So if I want to do x equal to the fourth root of negative 16, I'm not going to get a real solution back out, right? This would actually be like 4i, no, 2i. But again, I don't even really want to talk about it because I don't even want you guys to even write them down as solutions, because in this course we do not see them. They are imaginary. So our response to that is no real solution. There is a solution. It does exist. I'm not divided by zero. That's like never allowed anywhere. But there is a solution, just not in the realm that we're talking about. It's in a different universe, if you want to think about it like that. Okay? So no real solution. Oh, let me box my answers. Did I do that? Ah. Okay. And really, I'm emphasizing the real part. Okay? So let's do some more level up power equations. Okay? So we're going to solve x squared minus 5. So similar to the linear equations, I want to get x alone. So I'm going to caboot 5 over, so plus 5. X squared equals positive 5, all right? And then I'm going to take the square root of both sides. So that x will give me plus or minus square root of 5, okay? Because I'm taking an even root. So you can even tack it on in there if you want. I didn't, just because I don't want you to also put it here and then divide, gets confusing. All right. So you're like, Bo, but 5 doesn't, the square root of 5 is, but just leave it square root of 5. Don't use your calculator. Stop doing that. It's more than acceptable to just write it like that. That is more correct than telling me this is 2.1 something. Actually, I'm curious now because I want to see how close it was. I was going to say 2.147. That is my intuition. Root 5. 2.23. Okay. Alrighty. So next one. Ooh, let me under. If you tell me that it's just square root of 5 and not plus or minus square root of 5, you're only giving me half of the correct answer. So how can I give you full credit if you don't give me all the solutions? Just think about that. All right. So now we have in number 2, x minus 4, that quantity squared equal to 5. So now we have a little bit on that something else squared, not just x anymore. Do not, in this case, FOIL. Don't multiply out. Oh, no. You're already set up for a much, much easier problem if something is squared like this. And we'll talk about this more actually in super duper detail. It's whatever. Foreshadowing to C2. So x minus 4 squared equal to 5. When you're solving equations, you're doing reverse PEMDAS. Yeah. So I'm going to need to work my inside out, right? So even though the stuff in parentheses is happening, I can really only work with what's on the outside, this exponent first. So instead of doing parentheses and exponents, we're doing exponents, and then we'll work on what's inside that parentheses. And then whatever's inside that parentheses works through PEMDAS on its own. I know some people didn't learn PEMDAS, and I've heard other ones like BEDMAS. It's like brackets instead of parentheses. It's wild. Anyways, so I'm going to square root each side equals square root of 5. And then this will yield x minus 4 plus or minus 5. And I understand, square root of 5. I understand the confusion of like, oh, won't this also be a plus or minus? Yes, but we're kind of taking that all into consideration with just putting it on the one side. I know that seems confusing, but just put it onto the side that doesn't have x involved, okay? So now I need to get rid of things that are added and subtracted from x. So to get rid of that 4, I'm going to add 4. And I can't add 4 to square plus or minus square root of 5. So all I'm going to do is write 4 plus or minus, because that plus or minus means plus or subtract, right? Add or subtract 5. And I've also seen some people write it like they'll do each one. X minus root 5, sorry, not X, 4 minus 5, or 4 plus 5, square root of 5. I think on WebAssign, since it doesn't have a plus or minus, it asks you to write it as a comma separated list. And that's what this means, like that. Read instructions. So these are all equivalent. I'm lazy, so I write it like that. And the reason, you could have also done plus or minus, another way of writing it, plus or minus square root of 5 plus 4, right? And the reason, I mean, you could add no, you can't. You can't add to the number inside of the square root like that. That doesn't work. So that's all you do. I like to write the thing in front of the root because I don't want to get confusing if something looks like it's inside of the square root. So just to be clear as possible. Okay, so moving on. So now we have x to the third, to the 3 equal to negative 8. So I'm going to do the cube root of each side. Is it okay if I take the cube root of negative 8? If your answer was yes, you are correct, because I'm taking an odd root. If I see an odd number in the exponent, my life becomes so much easier, right? So I get x equal to, oh, that's a negative number. So it's automatically just going to be negative. If it's a positive number, it's going to be positive. And then I think about, oh, what is the cube root of 8? It's 2. So then, and that's how we get negative 2. So those signs are going to match the negative 8 and the negative 2 for just the reasons that we've talked about before. Okay, I feel like I'm flying through these, but I'm kind of taking on the assumption that if you needed to write, you would just pause me. Okay, so now I have something multiplied by x to the 4th. All right, so we go through PEMDAS. So I want to deal with multiplication and division prior to dealing with my exponents. All right, so I need to 16 divided by 4, over 81. So I want to divide by 16. So I get x to the 4th, you're like 81 divided by 16. Like, I don't think that's going to give me, don't put it into your calculator and get a decimal. Gross. I don't want to see decimal answers. Ooh, that's what I'm going to do. No decimal answers. Okay. Ooh, look, there's decimals. So the next problem. You'll see why. So, I'm going to leave it as 81 over 16. Okay. I'm actually going to scoot up here. So now I want to do, right, I'll write it like this. Change it up, just doing same thing. Just writing it a little bit differently. So we'll raise everything to the 1/4. Beautiful. And then I get x to the 1. And then if you remember the rule about the exponents, they just go to the numerator and to the denominator, and there's no worry. So this would be like the 4th root of 81 and the 4th root of 16. So I know what you might be thinking. You're like, oh, wait, that should be plus or minus. Well, aren't those plus or minuses going to cancel out? No. There is a situation where I would have minus the 4th root of 81 and plus the 4th root of 16, or vice versa. One of them might be negative, or both of them might be negative, giving me a positive or negative answer depending on that. So I still have the possibility of getting a plus or minus. So right even up here, you can just put it right there if you want to. So my answer is still plus or minus. Just because I'm dividing by plus or minus divided by plus or minus, they don't cancel out necessarily. Okay, So the fourth root of 81, well, the square root of 81 is 9. Square root of 9 is 3. So 3. And then 16 is 2. So plus or minus 3/2. And you could check both of these by putting them into the original. You just have to check each one. Sounds pretty fun. Alrighty. So now we're going to talk about dealing with slightly different power equations, okay? So now I have these decimals. I have made the assumption that you can multiply up to one decimal place, not multiply, convert up to one decimal place to a fraction. And I think that is a very fair assumption. Because 0.1 is 1 over 10. So 0.2 is 2 over 10, right? That's the 10th place in, I hope you guys can see what I'm writing. That's the 10th place in the decimal, right? And then we can see 2 over 10 is the same as 1 over 5. That simplifies. I'm never going to give you 0.325. What? I don't know what that is. I think it's 3/8. So I'm never going to do that. I would only ever give you up to the one decimal place like I've done here. Okay? So getting rid of decimals. So get rid of decimals. So I'm going to do 0.6 is going to be 6 over 10 times x to the 2 over 10. And then I can simplify from there really quickly. So 3 equals 6 divided by 10 is 3/5. And 2/10 we just said was 1/5. Okay. So I need to get x by itself. So I need to multiply by, how do I get rid of the 3 and the 5, the 3/5? I can kind of do it in one step. So I'm going to multiply by the reciprocal of 3/5, which is 5/3. So times 5/3 times 5/3, 5, 5, 3, 3. These threes actually cancel out. So I'm just left with 5 equals x to the 1/5. Remember, I want x equals something. So I want x to have to the first power. So just like I have been raising each side to 1 over whatever the exponent is, I'm going to say like raise to, it'd be like 1 over 1/5, which is just equal to 5. So I would do a 5 here and a 5 here. I wouldn't actually give you a number this big, so you definitely need to put this in my calculator. So I would get 5 to the 5, which is just 3,125. Okay, so the reason I'm doing it to the 5 is because I want to do the reciprocal of whatever the exponent of whatever the power of x is. It was 1/5, so 1 over 1/5 is the same as 5. Reciprocal, you just numerator, denominator, switch. Okay? And so I can even write x equals 3,125. So it's like super clear. Okay? Let me check what it okay, we only have like 3 more questions. My pin is telling me that my power is low. Okay? So that's how we can go from decimals to a beautiful answer like this. I change my decimal into fractions. I then multiply by 5/3 to move it over. I can't always get rid of every fraction, right? I have fractions in the exponent, and I get rid of those later by raising each side to the reciprocal of that fraction. Okay, so now what if I have a negative exponent? So we've talked about positive whole exponents. Those are pretty fun. Fraction exponents we just saw, and now negative exponents. Okay, so there's multiple ways to deal with these. Um, and I'm going to go with my favorite way, which is kind of literally what we've been doing. Raise it to the 1 over the power, the reciprocal. Okay, so I need to get x alone first. So we're going to divide each side by 3. So we get x to the -5 equals 2/3. So then I want to raise each side to 1 over -5, which is the same as -1/5, right? I just moved the negative out front. So x to the -5 to the -1/5 to the -1/5. All right, so this is like multiple things going on at once. So when I have a negative in the exponent, what happens to this fraction? It flips, right? So this is going to be the same as 3/2 to the 1/5. So I'm just applying that negative first. All right. And then I can just rewrite that as, if I wanted to, this is a perfectly fine solution right there, to the 3/2. Some people will be like, oh, you can't have that in there. And then you have to rationalize it. I need to sneeze so badly. And so on and so forth. I had another light bulb went out. Okay. But this is perfectly fine like this. Both of these answers are beautiful. I'm fine with fractions being in the radical in this instance. Just make sure it's clear that it's in the radical. Okay. So we can also solve for, okay, so yeah, we talked about whole numbers, fractions, and negatives. And then we talked, the similar would apply if there was a negative fraction. All right. You guys will have practice problems on that. And I assume that from these problems, you can mush those things together and do a problem like that. I give you the tools, you solve the problems. Okay. So solving for one variable in terms of others. So in other fields, equations will involve more than one variable. If you're in chemistry, you know pivot, I don't know, something like that. And you often want one variable in terms of the other, like perfect gas laws. To do so, just treat other variables as numbers. So I have t times x equal to 2t plus 3x, and I want to solve in terms of x. So that means I want x equals. Okay. So I want an x equals answer. And I'm going to treat t as if it was like the number 4 or something. Doesn't matter. It's a number, and I wanted to get away from x so I can isolate x. So I would get everything that has an x in it onto one side. So tx equals 2t plus 3x. So this already has a 2t on it. So I'm going to subtract 3x from both sides. And I'm actually going to write tx minus 3x equals 2t. Because we don't know what t is, but it's still a number. But I just don't know what it is yet. 2t. There we go. Well, now on this side, each factor, remember each terms are separated by addition and subtraction, has an x in it. So I can pull that x out. That's the whole point of moving everything that has x involved onto one side. So then I can pull it out. So t minus 3 equals 2t. So right, I get a t left over in that one and a minus 3 left over in the second term. All right, cool. Now I have x times something equals something. So I need just x, so I'm going to divide. So divided by t minus 3 and t minus 3. So I'll get x equal to 2t t minus 3. And if you wanted to, you really could even plug it back up in here for x, and you would get something equal to something else. All right. Can still check. My pen is dying, or else I would do it. Yay. Okay, cool. Last problem. I know this section's been long. What time is it? Oh my God, it's almost 7. Oh. All right, cool. So Newton's law of gravity is F equals G times little m times big N over R squared. And we're asked to solve for big M. In this case, F is force, G is gravity. I think little m is mass, big M is momentum, and R is like a radius of something. Um, that's just a fun fact. You literally don't have to know that. So we're asked to solve for big M. So yeah, we can either be asked to solve in terms of x or solve for just this variable. So this is saying I want big M equals. Okay, so I'm gonna rewrite our equation. G little m big M over R squared. So if I wanted to, I could multiply. There's so many ways to solve this problem. I can multiply each side by R squared to get rid of that fraction. So I get R squared times F, G times little m, big M, and then I just want big M, so I'm going to divide by cap. If it's a capital, I would say like cap G or capital G, doesn't really matter. Little m onto both sides. And then M will be alone, just like we want it to be. All right, and it's just like that. I'm just shuffling around this equation from going from F equals to M equals by doing the same things that we did. We just don't have numbers this time, so I can't give an actual number answer. And it looks just like that. And you could write it F times R squared over little m times G. The order doesn't matter. It's all your preference. All right. So I hope that wasn't too long for you guys. You have one more section for today and then you're done. So I will see you there.